Good afternoon, everyone. It is actually a great pleasure to be invited by all of you, great scientists who have been there for me, before me, guiding me to be where I am today. And I really appreciate this opportunity. Thank you so much to Professor Cornell, who is the chair of the African Light Source, who has always looked for me to be involved in this work. And I am really very, very happy to be part of the whole organization. I'll speak on synchrotron radiation-based X-rays, X-ray studies, but then I want to make it clear that I realize that I'm speaking tomorrow and it was like I'm going to speak exactly the same thing, but I'll try not to be too technical now so that tomorrow I can become deeply technical. All right, thank you so much. I just want to remove this here, okay. Yes. World Synchrotron Radiation Facilities. If you look at this map, you can see that definitely in Africa, we don't have anything. And whilst we don't have anything in Africa, and all the people who have spoken about what is that you can do to move Africa forward, you look at USA, it has got 14, EU has got 17, UK has got 1, Japan 5, Russia 5, Italy 4, China 4, Singapore 1, Thailand 1, South Korea 1, and Brazil 1. And you realize that if we want to move forward in scientific research, we really need to invest in this synchrotron radiation. So my experience has been that if we go into newer techniques, we are able to find new solutions to world problems. And in particular in Africa, we are being always used as gimmicks for experimental work. And whilst we are doing that, we can do it ourselves. Omar, what about it now? Okay, right. We would want to have an African light source, and I just want to talk about what will be the advantages of having an African light source. According to the United Nations Sustainable Goals, we have issues with energy, equity, we have issues with food, we have issues with water, and we want to say that we'll be able to achieve that in the near future. And I wonder if that is possible. In the energy, water, food nexus, where everybody else in the world thinks that they should be bringing aid to Africa so that we can have food, whilst we have got so much land that we could be using to grow our own food, and so much water in the Congo River, for example, and energy, investing in renewable energy whilst we are doing our research. So the African light source has got very, very big advantages for us in Africa. And it will bring just one light source at one point, it will be able to bring us a multidisciplinary research facility. An example is what has been done at Berkeley Lab for COVID-19 and related diseases. They use the light source to find some results which they think are excellent results for COVID-19. And they use the advanced X-rays to map out the 3D structure of proteins relevant to diseases at a scale of molecules and atoms at these laboratories. At Argonne labs, they have used the Photon source, which is also a kind of a synchrotron radiation, a bright light for drug delivery, and they were able to use molecular X-ray discovery, crystallography, so that they can come closer to an effective HIV vaccine and addressing a number of diseases that are very rife here in Africa. So we started this journey with all like Professor Cornell going to a European synchrotron radiation facility. And I like what they've written on their website. They say they're unlocking the secrets of matter. the ESRF state-of-the-art in synchrotron provides the international scientific community with unique opportunities for the study of materials and matter, addressing global challenges like COVID-19. What's wrong? Can you hear me? Bringing nations together because it's an international facility. And South Africa is one of the countries that are collaborating with this synchrotron radiation Department of Science and Innovation. At this facility, using the high resolution near field synchrotron photographic X-ray, they were able to map out the 3D, the material was the ultrafine eutectic microstructure of titanium iron-based alloy. So this material was produced by additive manufacturing, exploiting the high solidification rates of laser-based 3D printing. And they were also able to do this one for the heart, the kidney. Three-dimensional image of kidney and unprecedented quality have been obtained with a simple, cost-effective of sandpaper as an optical element to X-ray imaging beamline. And when you are working with such, I believe that for us in Africa, we can be able to do something about all our problems, finding cures, bringing major breakthroughs in material science and life sciences. As what we're doing. We have visited this research facility, ELATRA, in Italy, and there are lots of opportunities for African students. One must just go into the ICTP website and go into the ELATRA website and be able to see the opportunities that are there. And also another organization called CISA there has got that kind of facility. And this kind of facilities will help us to reduce the African brain drain for our people who goes to Europe or to Americas to do a PhD, and they cannot come back because there are no facilities for them to continue with research. So this energy issue will give Africa an opportunity when we are continually investing in different research opportunities like this, the light source. So I'm looking forward to one day finding a light source in Africa, which can be very usable for all of us. In this picture here, you have got two storage facilities for solar energy. One is the batteries here, and the other one is hydrogen. And I am focused on hydrogen, but tomorrow I'll also speak more on both hydrogen and batteries. So what is synchrotron radiation? Synchrotron radiation is emitted by charged particles traveling at speed relative to the speed of light when accelerated by magnetic fields. So these were first observed in synchrotron and synchrotron light, now produced by storage rings and other special particle accelerators, typically accelerating electrons. And it is able to produce giga-electron volts of energy and lots of energy using the basic electromagnetic studies that we do in high school. This is a ring, you know, when you work with Zoom, you start doing wrong things. This is a ring that represents a light source in which electrons are. It's a cartoon that shows that electrons will be accelerated throughout here, interacting with the magnetic here, and storing the energy that is being created by this acceleration of electrons. So the experimental techniques and usage of this synchrotron light radiation. We all have XRDs in our vicinities where we can work, but these are very limiting. So synchrotron light is an ideal tool for many types of research in material science, physics, and chemistry. And it is used by researchers from academics, from government laboratories, and industrial places. We go to the synchrotron radiation facilities to explore the materials. Like here, when we're working with mining materials, you can take it to a synchrotron-based radiation facility where you'll be able to see more of what is contained in that material. So several methods take advantage of the high intensity, tunable wavelength, collimation, and polarization of synchrotron radiation at beam lines, which are designed for specific kinds of experiments. And I'll speak about these experiments now. One of those experiments is scattering and diffraction. So we know the XRD and scattering experiments are performed at synchrotrons for structural analysis of crystalline and amorphous materials. So this application to material science. So the measurements may be performed on powders, single crystals, or thin films. The resolution intensity of the synchrotron beam enables the measurements of scattering from dilute phases or analysis of residual stress. So XRD, X-ray crystallography of proteins and other macromolecules like PKX or MX are routinely performed when you are using diffraction and scattering experiments. And in 2009, the Nobel Prize in Chemistry was given to this kind of research. And that's where you find your SXF, which is a single angle X-ray scattering for nanomaterials, and also the grazing incident small angle X-ray scattering. So these are all done in the synchrotron facility. Oh. This is the application of a result of structure of ribosome, which actually won the Nobel Prize using the synchrotron facility. So we can also do spectroscopy where you do XF, or you do X-rays, or you do NEXAVs, and so many different related spectroscopies that are coming out of the synchrotron radiation. You know, I looked at the time, guys, and I saw 4:08. I thought it's 4:18, and I was scared. So we can also do imaging. Synchrotron X-rays can be used from traditional X-ray imaging, phase contrast X-ray imaging, and tomography. If you always regularly go to the lab like me, sometimes you get very frustrated that your image that you have found there is not very accurate. So you need to use a synchrotron facility like STXM and LIGA so that you can come up with very clear results, which we will be able to publish in very good journals. Like the previous speaker was speaking, that we need to be publishing in a high impact factor journals. Wow, this is my favorite, hydrogen fuel. We have seen that already hydrogen is being used as a fuel in many different transport facilities. During the pandemic, the aviation industry was brought to its knees. And I think that gave us an opportunity to look at how we can do research in a different way to solve economic problems in our countries, which are actually energy problems. And then we can go and do the storage of solar energy using hydrogen fuel. But the problem that is still there is that many countries don't even have one station for hydrogen refueling. That's why we'll stay for a long time using oil-based fossil fuels. And many people want to argue with you and say, but what are we going to do with oil? We have many other uses of oil, which will not contaminate our environment. Hydrogen, it's extremely important. You use it in vehicles, you use it in synthetic fuels, you know, upgrading oil, biomass. You find it so in many different business opportunities and scientific opportunities, as you can see in this picture. That is, you can take your hydrogen from using some technology into your grid and start feeding different areas so that everybody has got electricity due to hydrogen, not fossil fuels. And we can also use the solar to store our hydrogen. Store solar energy using hydrogen, sorry. These are the few fuel stations of hydrogen globally. Japan, that smallest country, still has the largest number of public hydrogen fuel stations. And Germany has got 60 and USA has got 42. Other countries don't even have at least one. And we must look at the future of storing hydrogen as a fuel for our transport so that we can clean the environment. So our case for hematite. Some years ago, me and my colleagues, my colleagues in Switzerland at EMPA published this paper called In Rust We Trust. Rust is the hematite, which is the red soil. And there they found, using synchrotron facility, they were able to observe 2 electron holes in hematite during photoelectrochemical water splitting. Another experiment by my colleague Dibajay Bora and Arthur Brown, using the X-ray diffraction facility, were able to publish this work on evolution of structural properties of iron oxide nanoparticles during temperature treatment at the Synchrotron facility. And evolution, the next one was evolution of oxygen near edge X-ray absorption fine structure, transition in the upper Hobart band, where we were using the material in iron oxide for electrochemical oxidation. All right, this is the process for photoelectrochemical water splitting. You shine the sun on your semiconductor, which is a phonoanode, and then you create electron hole pairs where electrons are attracted by a bias to the platinum counter electrode. And then this blue here is the water. And we say at the photoanode, the hydrogen, the oxygen is involved, and then at the counter electrode, that's where we produce hydrogen. That's why we speak about water splitting. We take energy and we apply it into water using the device that comes from a semiconductor and a platinum electrode, and you produce oxygen and hydrogen. What you are going to do is oxygen, you throw it in the atmosphere, you reduce the amount of carbon dioxide that is already destroying our environment, and you collect hydrogen for your transport issues. So our material that we want to use, that we are using in my lab, is hematite for photoelectrochemical water splitting. Semiconductors that are being used here have got certain requirements. It must have a suitable band gap to be able to absorb the solar light, and it must have suitable band positions, which I'll explain quickly, and then it must have low overpotentials and efficient charge transport and stability in water. When we look at the band gap, you find that actually natural solar radiation consists of 5% ultraviolet light. So it becomes difficult for you to use a material with a bigger band gap, a band gap that absorbs in the ultraviolet light, 43% in the visible, which takes most of this, and that's what we need and 52% in infrared radiation. So these are the band positions. That's your conduction band, and that's your valence band. This is your hydrogen production position, and that's your oxygen production position. You must be able to find a material amongst all of these materials that you see here. People have used them and they are published. But when you look at them and you look at the band gaps, silicon has got a nice band gap, but it is not stable in water. Cadmium selenium, it has got a problem of cadmium will be dissolving easily in water and is poisonous. Silicon carbide is too wide. Gallium arsenide is suitable, but gallium arsenide is not stable in water. And then zinc oxide may be a bit stable in water, but the band gap is too big, so it will absorb very little of the solar energy. We are trying copper oxide, but copper oxide is not stable at all. The most attractive material amongst this is iron oxide, which we call hematite, which has got a band gap of 2 electron volts, which will absorb almost 40% of the visible light, and it is stable in water. A simple illustration of how iron oxide is stable in water is that if you go to any place where there's nice flowing water, like a river where it's not very deep, you'll find stones in there. And those stones on their surfaces is iron oxide. And the iron oxide is able actually to grow algae on top of them, which means that iron oxide is very stable in water, but iron oxide has got its own other problems. And let me just quickly run because now I'm running out of time. So I will speak about these things more tomorrow. So when you look at iron oxide, hematite, the advantage is that it has got that small band gap, is relatively abundant, therefore it is cheaper to use, it's chemically stable in aqueous environments, and it has got a suitable position for oxygen evolution reaction. And the disadvantages is that it is a poor conductor of electricity. It has got its short lifetime of excited carrier charges, poor oxygen evolution reaction kinetics, and a very short diffusion length. And what happens with the very short diffusion length is that iron oxide, when electron hole pairs are created, they will recombine very quick. So we have made this iron oxide using solution-based method, hydrothermal method, spray pyrolysis, and all of that. And we have built this in our lab. We have them in our lab. We have found that if you use nanostructuring, doping, heterostructures, modification with co-catalysts, and the plasmonic enhancement with metal nanoparticles, we are able to improve photocurrent using hematite. Therefore, whilst we are improving hematite photocurrent, we are still putting together a good review that will show that this nanostructuring, which should be used in the hematite, as you grow hematite to produce nanostructures, that you can go to your synchrotron radiation and see the finer structures of these nanostructures. And other people like Kevin Sevula have done that with Dibaje Bora and Michael Gratzer whilst we're using it for hydrogen production. These are the nanostructures that we have achieved in our labs: the dendrites, nanoparticles, mesoporous phases using deep coating, the cauliflowers, the nanocones, and all of this. Whilst we have achieved them in our lab, we don't claim that we are the first people to achieve that. Other people have achieved that. Chair, how much time do I still have?
You have a total of 9 minutes left. Of that, you may want to leave time for a few questions.
Thank you. I was just worried that I don't have to take a lot of time. So we have prepared hematite, and then the photocurrent density. We have looked at the photocurrent. These are our results in our lab. For the bulk hematite using electrodeposition, the photocurrent was 0.5 volts versus mercury hydrogen oxide in 1 mole of sodium hydroxide with applications of 1 sun. And in all of this, we have used 1 sun from our solar, okay, whatever. Then we have also achieved nanoparticles, and you can see that our photocurrent is growing gradually from the 0.5 milliamps, 0.9 milliamps, 1.3 when you use nanorods, after we have grown those nanorods using hydrothermal methods. And then with our nanoflakes, we have just achieved an experiment where we have made the nanoflakes, but the photocurrent is too small. But another experiment in the lab where we used the nanoflakes, it was improved a little bit, but we still believe that the nanotubes and the nanorods are doing better as compared to other nanoparticles. When you use suitable impurities to dope your hematite, you find that you are able to improve the photocurrent output of the hematite nanostructures. We have used manganese, we have used gold, we have used sulfur, we have used phosphorus. And in all of this, we have found that the photocurrent is changing in differently in milliamps per centimeter squared, with the highest photocurrent being 0.74 when we have doped with sulfur, but we have not yet proved whether this with sulfur is not poisonous, or will it be able to succumb the damp environments where we are using our devices. Okay, let me just quickly run. We have used the catalysts like iridium oxide, and we have co-doped with cobalt, and this is actually platinum, sorry. And then borates like nickel, bismuth, and oxyhydroxides. So in plasmonics effects, we have deposited nanoparticles and metal nanoparticles onto the hematite and studied the Schottky barrier behaviors of the photoelectrochemical device, which we will now put in water and look at if we are improving in that kind of work. So the work that we have done in our lab is when we were varying the different methods with using either deep coating or spin coating or combining the two. And the results, let me just go to the photocurrent results. You can see that when you have used the deep coating, what is that? The deep coating is here in A, and then deep spin coating is in B, and then combined spin coating, deep coating methods were not giving us best results. They were very bad. But then if you take one of the two, you find that you are doing much better. Another experiment is that we have established in our lab the electrochemical impedance spectroscopy, where we are able to do measurements on the impedance spectroscopy measurements for the hematite in water or in a aqueous solution. And we are able to produce very nice results that you can see here for dark measurements and for the light measurements using either a combined coating and deep coated methods. Many of the people out there are still using only deep coating methods, and we have published this paper on influence of coating techniques on the optical properties and structural properties of hematite thin films. The other one was how we made our nanostructures, as you see it here. I just want to rush quickly. And then the pictures here shows you that we're able to find the nanostructures with very little diameters, like 31.2 for this materials, hematite. And then we did the annealing studies. And then in the annealing, as you see here, we have used our normal XRD, and we would be very happy to go to a synchrotron facility and do these measurements again and see what we get in situ measurements when we are using this. When we did our annealing studies, we found that you can anneal hematite from 500 to 750, but if you go to 800, something else happens, which is an example of the dislocations becoming bad in this material when you anneal at a higher temperature, so that there is traps and defects that are trapping electrons during the electrochemical measurements.
Dr. Diale, we are down to the last 3 minutes and you have many questions in the chat. So if we can wrap up a little bit sooner.
Okay, let me wrap up this and not go further beyond this. Let me say we have achieved copper oxide onto hematite as a heterojunction structure. And yeah, our photocurrent continues to improve. So these are our list of publications for all the work that we have done in the past since 2014 up to now. We have been doing this research since 2014, but we started publishing actually, I think in 2016. I want to say in summary, if you want to use hematite, strategies for nanostructuring are very important. And there is deep coating, and there's photocurrent measurements that improves as you use these different strategies. And then we believe that with heterostructures, with copper oxide, when we have established that copper oxide is stable, we can do much better. You know, I call it CuO, copper oxide, that way, because, you know, I'm not a chemist. I continue to do all those wrong things. I just want to acknowledge the University of Pretoria for giving me the enabling environment to grow in the research that I've done for water splitting and producing hydrogen, the National Research Foundation, which is funding my chair, and the Motsepe Foundation that is giving me private money. Thank you. Thank you for listening, everyone.
And thank you for a very wonderful talk. You have many questions in the comments. In the interest of time, and I realize I ran over by 5 minutes. I told you a time that was longer by 5 minutes than published. We will just run the entire session over by 5 additional minutes. I'm going to ask that Dr. Asmaret Bura begin to share her slides for the next talk, while we will take one question from the chat. One question from Daniel Wamwangi is saying, great talk, Dr. Diale. What are your thoughts on multiferroic materials such as bismuth ferrous oxide as thin films with large surface to volume ratios? If you can comment on that in just a few remarks.
Can I see the question, please? What is the chat? Oh, okay, it's here. Daniel, how are you? I'm good to hear. You know, you are such my neighbor, but you know, it's difficult to see each other.
Okay, yes, I placed the question into the chat, and it comes from Daniel Wamwangi, and it says, it asks you your thoughts on multiferroic bismuth ferrous oxide.
Oh, okay, on bismuth. Bismuth has achieved some kind of a photocurrent, but it has not been good with hematite due to its position for band gap alignment for hydrogen production. If you look at my slides, I think somewhere in that big, let me see, where is that slide? sorry everyone, that there's a slide, okay, that we just, yeah, this one. Okay, we can close this chart from here. How do we do it? Oh my.
Take your time to figure that out. Just go to slideshow, I think. Go to play at the far right. I think you have a play button at the upper far.
Okay, thanks. Bismuth has not been used here, but with the dope, when vanadium oxide is doped with bismuth, that's when people have reported something there. But because of its position very far from hydrogen evolution band gap and also very far from oxygen evolution band gap, it is still found to be non-suitable. But we hope your guidance can help us to make bismuth oxide, but we will make it a heterostructure with the hematite. I'm just sold out to hematite.
Okay, well, we thank you again for a very wonderful talk, and you will see in the chat window, there are many compliments to your talk.